Hello, everyone. I'd like to welcome you to our September webinar. This is part of a webinar series designed for the Critical Materials Innovation Hub for and by the Hub. I'd like to tell you a little bit about the webinar series. It's hosted by Colorado School of Mines, and we're always looking for new topics. So if you have a suggested topic, again, because these are designed for you, we'd love to hear your suggestion, and you can actually include that on the exit survey or email us at cmi@mines.edu. I do want to remind you that this is a public webinar, and a recording is going to be available next week at aimslab.gov/CMI. And you're going to look under the webinar menu, and we also have a YouTube and a YouTube channel. So please do, if you want to hear it again, join us again via our online at our website. Questions. We're going to hold questions till the end of the presentation. They can be typed in the Q&A box at any time. I really want to encourage you, as soon as you have that question, to go ahead and type it so that we can actually have some questions in the queue. And again, they're going to be answered at the very end of the presentation. Now I'd like to introduce our guests today. First, I'd like to introduce Thomas Tarka. Tom is a senior engineer at in the National Energy Technology Laboratory Research and Innovation Center. He serves as the director of DOE's Minerals to Materials Supply Chain Research Facility, Metallic. And he's also a technical director of the Process Optimization and Modeling for Mineral Sustainability, PrOMMiS, and you're going to be hearing more about that today. Also sharing the presentation gig here is Alexander Dowling. Alex is an associate professor in chemical and biomolecular engineering at the University of Notre Dame with a concurrent appointment in applied and computational mathematics and statistics. And he has multidisciplinary research abilities, and it combines chemical engineering, computational optimization, machine learning, and data science. And I don't want to take any more time from our presenters. And Tom, would you take it away from here?
Thank you, Cynthia.
You're welcome.
Good afternoon and good morning. I'm Tom Tarka from the National Energy Technology Laboratory. And today I'm here with Professor Alex Dowling for Notre Dame to tell you about PrOMMiS. PrOMMiS is a relatively new initiative that is focused on accelerating critical minerals and materials technology development. It's funded by it's an open source software effort funded under the Bipartisan Infrastructure Law. What is PrOMMiS? It's the application of an existing open source modeling platform, the IDEAS integrated platform, to critical minerals and materials. And the focus of PrOMMiS is basically to provide both process modeling and analysis capabilities, both techno-economic analysis and life cycle analysis. Along with those, the ability to optimize process configurations over multiple criteria, such as minimizing acid consumption or minimizing energy consumption of your flow sheet. And more broadly, it provides the ability to compress developmental timeframes through process screening, the ability to reduce the technical risk of scale-up and deployment, and really get the most out of pilot and demonstration campaigns, which we know can be expensive. So PrOMMiS is really unique in its ability to do those things. Next slide. Thank you, Alex. PrOMMiS really builds upon PrOMMiS builds upon previous investments by the Department of Energy. So it builds upon over a decade of investments from the Office of Energy Efficiency and Renewable Energy in the Critical Materials Innovation Hub, and also the Office of Fossil Energy and Carbon Management in diversifying supplies of new critical minerals. And what you may not be as familiar on is it builds upon open source modeling efforts funded also by FECM, specifically the IDEAS, the Institute for Design of Advanced Energy Systems, and CCSI and CCSI-2 modeling platforms. IDEAS was really developed to help de-risk and mature carbon capture technologies So the CCSI stands for the Carbon Capture Simulation Initiative, or the Carbon Capture Simulation Initiative for Industry Impact. And we've had a great amount of success with CCSI in de-risking technologies as they scale up and working with industrial partners as they go into pilot campaigns to get the most out of to reduce uncertainty as they deploy those technologies and as they scale them up. Next slide, Alex. So when we sought to apply the IDEAS framework and expand it to critical minerals, the direction we received from our sponsors at the Office of Fossil Energy and Carbon Management, or FECM, was that this wasn't a modeling effort where we're going to spend 5 years to develop a new model that may have some applications at some point. They really wanted us to understand the urgency of the need to deploy new critical minerals and materials technologies. And so there's a real urgency to learn by doing and start with existing projects and existing technologies that are under development. We were urged to not to reinvent the wheel, so we wanted to leverage all existing models and partnerships that we have. And more importantly, we're focused on creating a long-term capability. So what we know about critical minerals and materials is what might be a critical mineral now may change in 6 months or 2 years. 2 years from now, we may have a completely different list of critical minerals, or new things may be critical. So the goal of PrOMMiS is to provide a flexible and foundational platform that we can leverage as we face new challenges in the future. We're also urged to really make sure this was not an FECM project. This was a project that was focused on leveraging all of the DOE investments, whether those were CMI investments, FECM investments, and really coordinating with the Critical Minerals Collaborative. Next slide, Alex. So the end goal, of course, of PrOMMiS is, next slide, to compress developmental timeframes. And ultimately, our goal is to support DOE investments and existing initiatives that are hyper-focused on technology maturation, unlocking different feedstocks. And another goal of FECM is waste minimization. So if we start off with a given feedstock, our goal is to use the whole buffalo or minimize the amount of waste generated and maximize the amount of value we get from that initial material. And PrOMMiS as a platform allows us to explore those application spaces and explore how to optimize and maximize the process flow sheets that we're designing and maximize the amount of material used. Next slide, Alex. So PrOMMiS is a relatively new effort and initiative. We've only been funded for about 18 months, a little less than, but in those 18 months, we've had some really major accomplishments so far. And those include developing an initial unit operation and process modeling framework and library. We've actually completed the modeling of one flow sheet that was a pilot plant funded by FECM. We've examined end-of-life magnet recycling pathways developed by CMI and been able to form a superstructure analysis of those pathways to identify an optimal path of unit operations to maximize the NPV. And we've also used it to really dive into how to optimize a candidate flow sheet configuration. And I'm going to hand it off to Alex now to do a deep dive into that work. And then I'll summarize at the end some of the work on process modeling and costing.
Thank you, Tom. So I'm going to kind of talk about, in PrOMMiS, some of our advanced modeling and optimization capabilities for membranes. And as Tom mentioned, PrOMMiS is less than 18 months old. So I'm going to blend some ongoing projects and previous projects that predated PrOMMiS, and then talk about how we're really leveraging those and the directions we're headed with PrOMMiS. So I'll present both PrOMMiS-funded activities and some other activities funded by National Science Foundation. So kind of to understand the importance of membranes, we need to ask ourselves, how are these critical minerals are recovered? And this can be done from a variety of sources, primary sources such as brines or ores, or recycled materials or secondary sources, such as recycled batteries or magnets. And no matter the source, there's some type of mining, whether it be pumping from an aquifer, harvesting from the earth, or harvesting spent materials. There's then pre-treatment. So this could be evaporative ponds, grinding, or disassembly, followed by an extraction step, which often involves some type of precipitation and leaching. And then traditionally, this is followed with conventional solvent-based technologies that do a lot of kind of Edisonian trial and error in the lab, and then piloting in these large cascades of settling tanks. And there's a couple issues with the status quo. So the first is a lot of these processes have really large physical footprints, and they also have really slow dynamics. And those slow dynamics are a challenge if you think about a supply chain that's rapidly evolving. So if you're thinking about a recycling application, maybe every batch of material that you get has a different composition. You want a process that can react to that. The second is these processes generate a huge amount of acidic and organic waste. And the third is that they have a huge solvent consumption. So kind of in these themes of minimizing waste and improving efficiency, there's a big opportunity for membranes that can help facilitate some of these separations. And hopefully I'll kind of convince you a principle underlying PrOMMiS and some of the work in my lab is this argument that we really need a multi-scale holistic perspective. So if you think about membranes, there's some phenomenal research being done at the molecular scale to think about new materials for membranes. Once you've engineered a new membrane, you need to test it. So there's opportunities to automate some experiments. And I'll highlight some cool things we're doing at Notre Dame on a related NSF project. Once you have experimental data, you can then build mathematical models, preferably grounded in engineering science. And then those models facilitate scale up and process optimization, and then ultimately scale up for infrastructure optimization. And really, critical materials in establishing circular supply chains is such a challenging problem that we really argue there's a need for this molecular systems perspective. If you're interested and you're coming to the AICG annual meeting, I'm helping co-organize a new topical conference that will be on critical materials and circular economies, and there'll be some PrOMMiS presentations in addition to a couple of CMI contributions. So kind of with this multi-scale picture, I want to offer 3 vignettes about opportunities, both kind of using PrOMMiS capabilities or related capabilities for this systems perspective to really help accelerate membrane technology for critical materials. So we'll start by thinking about materials design and manufacturing. So one opportunity for membranes is to do chemical patterning, where we have shown here is kind of a pore in a membrane, a cartoon of it, and we can functionalize this membrane and we can pattern it, and this will help have different properties that will facilitate different types of separations. So one way to do this is through additive manufacturing or 3D printing, where you're going to put an ink bubble on top of the membrane, and then we can have a diffusion, and then either a slow or a fast reaction. And for this, if you want to get really this nice pattern membrane where there's one active layer, then a second active layer, you really want a fast reaction. So this is a diffusion limited process. And we're going to refer to these as reactive inks, and they allow us to have nice control over this concentration gradient of functionalizing the pores. So the key questions are, how do you control this manufacturing process to achieve this while also minimizing the cost of these inks for various maybe environmental impact reasons or just economic reasons. So this particular system happens with a click chemistry. It happens in 3 steps where we have ascorbic acid helping form a copper complex. We then have our second step where we form this complex. And then this third step is actually where we're doing this click chemistry that we're reacting on the membrane surface. And if we have too much copper in the system, it's both expensive, so it's a waste, and there's human health and environmental concerns if that waste is not properly handled. So the question is, how do you formulate this ink to minimize copper usage while maintaining enough to have a fast reaction? So what we did is we put together a modeling framework that contains science-based digital models with experiments, and we really thought carefully about what are the governing phenomena happening, how do you model the reaction network, how do you model the transport, how do you accumulate data. We're then able to do parameter estimation and uncertainty quantification, so build a PD reaction diffusion model, and then use that to optimize the formulation of this ink, and then we could actually experimentally demonstrate it. So this is a great example of how you can use modeling and combine it with data to really drive experiments. And this kind of starts introducing some of the importance of building models and calibrating those models from data. And this plot here kind of shows the uncertainty in these two parameters in the model that we're inferring. So that's one example of how modeling, kind of at a more fundamental level, can help us to mature our technology. So let's say we've come up with a membrane. We're really excited about it. How do we gather the necessary data to then quickly scale up? And this is where there's a lot of great opportunities in automation and self-driving laboratories. So if you've maybe been following some of the recent news in the scientific community over the last 5 years, there's a lot of excitement around self-driving laboratories. And the idea is that we're going to have some type of robotic system that's going to combine with some type of intelligence system that's going to recommend and execute experiments in a repeatable way. And there's been lots of great demonstrations of this, especially in the material science community. So one example that I like, the artificial chemist out of North Carolina State University, is using machine learning models to kind of predict steps in manufacturing quantum dots, and then using that in developing a self-driving laboratory. So we've built on some of these capabilities in my group at Notre Dame, thinking about problems where you have to co-optimize materials and manufacturing together. And I'm a chemical engineer. I really prefer phenomenological models, so like that reaction diffusion model, whenever it's possible. But there's some projects where you just don't have the time or the budget to develop a phenomenological model. What can you do? And one option is to do derivative-free Bayesian optimization. So this is going to be building data-driven models, specifically Gaussian process models. And Gaussian process models are inherently stochastic. So that's really nice for modeling noisy experiments. They work well with really limited data sets. And they also work well if you have about order 10 decisions. So we've applied this in the context of ink formulation and additive manufacturing for thermoelectric materials, and have a whole sequence of papers based on this. And this is one way to help accelerate that optimization. So it's to kind of complement the mechanistic that we talked about in the first example with a pure data-driven. And to give one vignette of this, this is multi-objective Bayesian optimization for plasma sintering. The question is, how do you optimize the sintering process where there's decisions like applied voltages and how this pulse signal works? And what we were able to do is develop a Gaussian process model that predicts this output. For the first step of the sintering process, if we want to maximize the SEI, which is the specific energy, there's 3 key variables: a jet flow rate, an input frequency, and then the applied voltage. So these are showing slices of those 3 variables. The colors are showing the expected improvement. So on average, how much do we expect this figure of merit will improve? What this plot here is showing in the animation is, as we do these Bayesian optimization rounds, how this best figure of merit that we get in each iteration increases. And I really like this plot because it was my graduate student and another graduate student who went to the lab together, and you see this huge uptick in performance that was in one afternoon, where this Gaussian process model was guiding the experiments and double the performance. We then took it a step further and were able to look at trade-offs between something like electrical conductivity and the maximum peak temperature, and use these data-driven models to predict this Pareto optimal trade-off and really understand how much performance we were sacrificing in terms of electrical conductivity as we limited our peak substrate temperature, or as we changed the manufacturing time. So if we constrained it to be 60 minutes versus 30 minutes. So that's what you can do with systems that are modestly small and are really amenable to these low data machine learning models. But often, in the context of critical materials or membranes, we actually can write down a mathematical model that's grounded in engineering science. So complementary to the self-driving labs are these ideas of digital twins and combining automation and model and design of experiments. And we've seen this in chemical engineering a lot in the context of reaction engineering, where it's a pretty complicated dynamical system. It's pretty hard to develop data-driven models with really small data sets. So instead, we're going to build models that are grounded in engineering science. And my opinion is, if we want to do self-driving laboratories for complex materials like membranes, we're going to need to leverage these science-based models because they're a lot more data efficient. So a natural question you could ask is, how would you build science-based models? So what's the workflow? And the way this works is we start with some prior knowledge in data. We can then postulate one or more mathematical models. PrOMMiS is built on IDEAS, which is built on the Pymo ecosystem. So this is a modeling environment that's really amenable to optimization. And there's a tool to postulate PDE constrained models. And when we postulate models, maybe we are going to ask ourselves the question, well, which model is actually the most justified by the data? We can then do measurement optimization. So we can ask which measurements are most valuable, followed by parameter estimation, where we're calibrating parameters in the model and quantifying their uncertainty. And then we can do sensitivity analysis and ask ourselves, how does the uncertainty that came from our measurement data propagate into our model, propagate into the model predictions? If that uncertainty is too great, we can then do model-based or science-based design of experiments, where we solve an optimization problem to decide what experimental conditions are most valuable. And then we get new data and we repeat the process. And ultimately, this is going to spit out a model with quantified uncertainty that we can use for that process design and scale up. So a key capability inside PrOMMiS is this workflow and doing this sequential model-based design of experiments that leverages some really nice computational optimization capabilities that DOE has invested in the last 10 years. So my groups used science-based design of experiments extensively, and it's really a great framework to help guide collaborations, whether this be carbon capture, whether this be thermoelectric materials, thermodynamic modeling, or membrane characterization. So to kind of help show how this is helpful, I want to focus on the membrane example. And this is with a collaborator here at Notre Dame, where we've developed this new capability to characterize membranes faster. And this is using a diafiltration cell. So there's a nice animation. Let's see if it works. All right. So we're going to start by applying a pressure here. And we have this diafiltrate filled with diafiltrate, so like an aqueous solution. That diafiltrate's then going to get pushed into our stirred cell and mix with the holdup in our stirred cell. And a membrane is right here. And this membrane is going to perform a selective separation. So we're going to be able to collect conductivity data both on the retentate side and the permeate side. The permeate's then going to flow through to these scintillation vials. And then we can record in the scintillation vial the mass. And this actually rotates. I have a video in a minute to facilitate total automation. So the question becomes, from a modeling perspective, how do you take this dynamic pressure, conductivity, mass, and sample conductivity data, and how do you use it to build a model really efficiently? So this is where the science-based data analytics comes in. I'm stripped away most of the math for this talk. I'm happy to discuss it in the Q&A. But we postulate a mathematical model that captures the solute and water flux. And inside this model, we want to estimate parameters like B, LP, and sigma. We can do that really well, again, leveraging PyOmo and other modeling tools. And we see really nice agreement between our model and our mass data. So we're thinking about extensions for charge membranes, many species, and then being able to do model discrimination. There's lots of opportunities to push this forward, thinking about uncertainty quantification, machine learning to do faster calculations, and ultimately we want to have a real-time digital twin. So to really appreciate why this automation is so helpful, I want to share 2 slides that come from my collaborator, Bill Phillip, and his super talented students. So typically in the membrane community, to characterize a membrane, you'd maybe do 10 filtration experiments. Both are 4.5 hours each, so you have a total time of 45 hours. And this kind of shows an animation, so we can see this sample changer, and this allows the experiment to be automated. We also have interface, and there's even a interface to text messaging that'll tell my colleagues' students when an experiment's begun, when it's going to complete, and when it's done. So it tells them when to get back into the lab. So when we add in this diafiltrate retentate probe, we got an experiment. When we do automation, we've cut this down to 2.5 hours. And we've worked on adding this new retentate probe and analyzing from a data science perspective how much extra information we're gaining from this additional measurement and how much that reduces the uncertainty in our model. You can see these probes shown here. And taking it all together with this automation and with developing this new sensor that was informed by the data analytics, we took a typical experimental campaign that would take 45 minutes, or 45 hours, I'm sorry, and really cut it down into 40 minutes. So this means a lot higher quality data that's more repeatable, a lot faster. So that we have ways to accelerate how you collect data, and we have ways to take that data and build mathematical models. How do you use those models for process design? So a really common way to do this in the systems engineering community, and we leverage these ideas in PrOMMiS, is to postulate a superstructure. So this is a superstructure for an N-stage cascade, or about three cascades are shown in this picture. Each stage can be subdivided into elements. And all these lines show the potential connectivity in the system. And then we perform optimization. And when we do optimization, we get out some really nice results. So this figure is really busy, but I have the time. I want to walk through it slowly. So each of these colored lines is a series of dots. Each dot is an optimal solution. So shown here are 3 solutions, 1, 2, and 3. Those correspond to 3 different process configurations or 3 different designs, 3 different recycle strategies. And you can see each of these 3 designs is encoded in the superstructure, and we start with the superstructure and we delete all the streams that have zero flow rates. And what we're showing on the X and the Y axis is the recovery that we get of lithium and the recovery that we get from cobalt. So what we're doing is we're resolving this optimization problem about 1,000 times. And we're plotting how this trade-off, this Pareto optimal trade-off between recovery and cobalt changes. So if I change my requirement for recovery and I of lithium and I maximize my cobalt recovery, how high can I go? The other great thing about this analysis is we repeated it for multiple stages. So shown here is 1, 3, up to 10 stages. And as you can see, adding more and more stages shifts the Pareto curve and allows you to have a better performing system. And this is really important because in the membrane community, it's really common for people to analyze a single stage and conclude erroneously that this is a materials problem. But if you do a little bit of process engineering and you think about a stage separation, you see something that you might conclude is a materials problem is actually a process problem. And there's the research questions are really in how you do that scale up. In this type of analysis, you do building models that came from those automated experiments. So PrOMMiS took this work, which has been published, and is building on it in 3 directions in this past year. So the first has been my student, Molly, who's focused on really extending these models. So capturing more sophisticated transport, connecting these models more directly with the automated experiments, and really helping understand what model complexity is needed to accurately capture the physics of the system while being computationally tractable. We're also building in these models into the PrOMMiS ecosystem, including rigorous costing, so we can move from having trade-offs between recoveries to actually understanding how material properties impact things like process economics or waste. A second extension being done by Jason at Carnegie Mellon is thinking about optimization under uncertainty. So started with this cascade. Jason has done some really nice extensions of it to connect this model a little bit more closely with a membrane system that you'd actually design and that you could actually build. And then thinking about how do you make these designs in such a way that they're robust to various forms of uncertainty. So we've thought about uncertainty in terms of if there's variability in the membrane in the membrane properties due to manufacturing. What performance do you need to sacrifice at the system scale to have enough flexibility to handle manufacturing variability? We've also started to think about variability in terms of feed composition. So if you're imagining a critical material recycling facility, every batch is going to have probably slightly different feeds. You'd want a process that's able to react to that variability. And we can capture all of this with a pretty sophisticated optimization framework. And then the third extension that we did, and this was led by Norman at Carnegie Mellon, was taking the same cascade, but instead of making all these decisions continuous and allowing for these pretty complicated designs, having discrete decisions. And realizing from a manufacturing point of view, if you had a membrane module, you'd really only want to have feed at the beginning or the end. Or if you were to put feed in the middle, it really needs to be one spot in the middle, and all these practical considerations. So Norman did some really nice work deploying some advanced optimization capabilities that consider these discrete decisions and was able to show that we can reproduce these results. And this idea of optimization with logic-based superstructures we're leveraging in other parts of PrOMMiS, including solvent extraction. So kind of the takeaways from the membrane perspective, and I'll throw it back to Tom after this, is these digital toolkits, whether it be all the way from data-driven optimization to automating experiments to model-based data analytics to process optimization. They can really accelerate technology development. We can guide materials design and manufacturing. We can minimize the experimental effort by being able to, in a statistically rigorous way, quantify which experiments and sensors have the most informative data. We can help de-risk technology by having a really rigorous treatment of uncertainty and doing optimization under uncertainty. And ultimately, we can have bidirectional feedback. So go from bottom up. If you come along with a really new innovative material property, how do you rapidly go and understand potential for impact at scale? Or from top down, how can you take infrastructure level goals, perhaps the amount of circularity, and propagate that back down to material targets? So thinking a lot more holistically about accelerating our research. So with that, I want to toss the conversation back to Tom to tell you more about capabilities and PrOMMiS beyond membranes.
Thanks, Alex. This is just so exciting, this work. And I think you've given just a flavor for the potential of PrOMMiS and what we've been able to achieve in a short amount of time. So now I'm going to talk a little bit about the core model framework and the costing. This is really speaking to the ability to do detailed process modeling and optimization. And then I'll speak to one other example just to give you a little bit of a teaser for a future webinar, probably. Next slide, Alex. So when we think about adapting an open source modeling framework to a new research area, we have to start by building unit operations. We have to start looking at property packages. And what's unique about critical mineral systems are that the data is, and the industry is rather opaque. So there's not necessarily a lot of data on some of the unit operations. Some of the unit operation designs are more art than science. And in addition to that, the property models, the different types of contaminants or the concentrations of different components can vary wildly from what we're used to modeling in say, a power plant or a traditional energy system. And so when we first started with PrOMMiS, it was a bit of a challenge because some of the feedstocks we're looking at have concentrations in the parts per million or parts per billion, and that's a rounding error in some of our previous modeling efforts. So we were really starting from scratch, and the first thing we did was we performed a gap analysis. We looked at several pilot plants, demonstration plants, and also commercial mineral processing flow sheets, and did a gap analysis to determine what are the common unit operations, what are the unit operations that are going to be really hard to model, and what are the unit operations that we're going to need regardless of the flow sheet that we identify or the flow sheet we want to model. Similarly, and in parallel to that, we looked at open source and other property packages that we might need to use or we might have available to us. And we were able to identify a number of unit operations to develop the first generation of models for. So you can see here the models that the unit operation models that we've developed so far, and these are all in the GitHub repository. In addition to that, we have WaterTap, which is another extension of IDEAS. And WaterTap is funded by the National Alliance for Water Innovation, which is really focused on desalination and water cleanup. And so we had already extended IDEAS to model water systems, and that's called WaterTap. And the WaterTap models provided us a basis for some of the critical mineral processes that we might need. And so you can see them here on the right. They range from reverse osmosis to ion exchange, nanofiltration, membrane distillation, et cetera. And then as you can see from property packages, so far we've integrated Freaksy, which is also available open source, and that was developed, I believe, by the USGS. And we're also looking at other packages. I will note here that we have the ability to do surrogate modeling and tap into other models. So where there are commercial packages, we're able to run those commercial packages and develop model surrogates that we can tap into for select areas that we might be interested in, select process operating ranges or concentration ranges. Next slide, Alex. In addition to that, we've developed the costing framework for PrOMMiS. And so that started with just the standard look at capital and operating costs for those unit operations, but also expanding that into annualized cost, revenue models, and developing some custom costing models. In addition, so that the goal of these are to provide the ability to do a techno-economic analysis. In addition to that, NETL has spent a lot of time in developing cost frameworks and consistent guidelines for costing and evaluating energy systems. So we're developing those and leveraging those for the PrOMMiS model development. In some cases, these have been top-down cost estimations, and we've used those to bound the cost of certain unit operations. But by and large, we're starting from bottom up. And we've leveraged everything from reported pilot data to data that's been reported in the literature or otherwise. As you can see here, one thing that we're looking to expand into is really understanding what type of incentives might be required for creating other value streams and whatnot. An example would be if we're treating a brine and we're producing water and extracting lithium, maybe we want to extract another critical mineral from that brine, and we want to add a unit operation to extract that. And so a really interesting question for our stakeholders and for us is, would it cost 5 additional, that maybe the process isn't economic right now, but if we had a tax incentive of $5 per kilogram or something like that, would that make it viable? So really understanding how to optimize the number of byproducts produced, what the additional costs would be, and how to screen different flow sheets for different product slates is really important to us. We're also building lifecycle analysis capabilities into this, and that's going to allow us the ability to do other multi-criteria analysis. Next slide, please, Alex. And here's just a brief overview. I'm not going to go into all of these, but these are the unit operations that we have cost models for so far. Next slide. And this is just a teaser. Alex alluded to superstructure optimization. And so one of the really powerful capabilities of PrOMMiS and the IDEAS framework is to do superstructure screening. So in this case, we looked at, this is Anna Torres's group at Carnegie Mellon and her student, Chris. We looked at the ability to recycle end-of-life hard drives, and then we expanded this work, they expanded this work into looking at a number of end-of-life products, so also magnets from electric vehicles and others, and looked at the 4 or 5 different areas of those processes. So you have disassembly, demagnetization, leaching and extraction, and precipitation calcination. And as you can see here, the potential flow of a process, of a material going through the process to produce a mixed rare earth oxide. And what they were able to do using this superstructure screening is identify what the most efficient and effective pathway would be. Next slide, Alex. And so lastly, and so that work was presented at FOCABD and will be presented, and those proceedings are available online. I can send the link if anyone is interested. But to close, PrOMMiS is an open source platform. You can see here how to get to the GitHub and download it. We're also starting up quarterly webinars to talk about the work that's being done. We do have teleconferences and quarterly meetings in addition to that. If you're interested in joining us, learning more about PrOMMiS, either tracking our status or learning more about software releases, please let us know. And I'd just like to thank you all for your attention and for coming to the webinar today. And I guess lastly, we have a really great team, and I'm floored by the amount of work that we've been able to accomplish over such a short period of time. I'd also like to thank our sponsors at the Office of Fossil Energy and Carbon Management.
And Alex, I want to thank you so much on behalf of CMI for this great presentation. And you held true to your promise of showing us things that can actually inform research and accelerate deployment. And we appreciated your examples of all your capabilities with the intent of better data faster. And we're all kind of in that boat and looking for those opportunities. I know there are a lot of people on this line right now who are thinking of, now how can we use them to, help further our research? So I'm sure there's going to be a lot of dialogue, but we have 3 questions open right now. So outside of, again, thanking you for such a great presentation, I'd like for you both to consider these questions, and if you'd read them out so that everybody can hear, and we'll keep moving forward here. And there's room for other questions for our audience out there as well.
Alex, do you want to grab that first question?
Yeah, so the first question, are the data derived from synthetic or natural brine compositions? I'm actually not sure which question this is, which part of the talk it's referring to. For the lithium cobalt superstructure example, that's actually thinking about battery recycling. So we've kind of looked up what typical feed streams would be. It's documented in the paper. For some of the diafiltration work, yeah, we were thinking about both brines and kind of executed experiments at a variety of compositions. So one of the key advantages of diafiltration is you can sweep over with one experiment a really large composition space, which gives you the data you need to build a model that you have high confidence in.
Yeah, and I'll add to that with regards to scope elsewhere in PrOMMiS. So we have looked at real compositions of brine processing. That's been focused primarily on water tap work, and that has not been expanded into critical minerals quite yet. We have started to develop process models and cost models for critical mineral recovery from produced water brines. One of the challenges is the multi-component nature of that, and the number of components in it that we have to deal with are a lot more when we're looking at critical mineral recovery as opposed to just desalination and whatnot. But that scope is in our scope for next year for PrOMMiS. And then Alex, I see the next question.
Yeah.
In slide 30. You want to grab it, or I can read it out loud?
No, I can do it. So in slide 30 shows the recovery of cobalt and lithium. Was this more about the grade of the cobalt stream versus the lithium stream? Also, what was the consideration for what's being lost? For example, was cobalt in the lithium stream? It was cobalt. Was it cobalt in the lithium stream that's considered unrecyclable? So that's a kind of great group of questions. So what we kind of had coming into this process was a lithium cobalt feed. We took the exact compositions actually in this paper. So these results are all from this paper. But we found a representative range for a feed from literature. And then the losses are, we can extract the cobalt-rich product, which is the retentate, from a variety of locations. And actually, that's a question in the superstructure. Where do you take out the cobalt-rich product? And then the permeate, which is the lithium-rich product, is always going to come out here. So depending on where you are on this curve, you'll either have more losses of lithium here or cobalt here. And actually, as you change your design decision, you change the trade-off between, do you want to recover more cobalt, which would mean really small losses here, or do you want to recover more lithium, which would mean small losses there? Shown in the paper, or the supporting information for the paper, we also show we also plot the solutions as looking at how, as you change the recovery of lithium, all the compositions in the streams change. So not just looking at recovery, but also looking at purity. So I think that kind of answers the question. And I want to emphasize this framework is really general, so it's easy to re-optimize with different feed conditions or optimize with uncertain feed conditions.
And I'll add to that. Oh, I just have one quick thing to add, Cynthia.
Perfect. Thank you.
One of the really interesting questions that we're starting to look at is, how do we optimize our separation processes, and what are the trade-offs? So is there the ability to remove unit operations? Can we use membranes or ion exchange to prevent the need for solvent extraction, which may be more costly? Can we do process intensification with membrane solvent extraction? And that may allow us to remove or reduce our operating costs and our acid consumption and environmental impacts. If we do that, how do we optimize for membrane lifetime? But really understanding and being able to screen optimal pathways for separation and or optimizing our product slate and the amount of products that we can produce is such an interesting and ripe area of research for these systems, and the ability to automate that process through PrOMMiS and our capabilities here, I think is going to really accelerate our ability to develop these new processes that aren't just focused on one product, and reduce the cost of producing additional products that may be of interest.
I want to thank both of you again for a great presentation. I know there are going to be individuals, getting a hold of you, and they can do that through our CMI hub. Also, I want to remind everybody that this recording will be available next week at aimslab.gov/CMI. Also on the Critical Materials Innovation Hub YouTube channel. So you'll have access to information again. I'd like to please join us, have you join us on October 15th when Frank Roberto from Newmark Corporation will present lithium-ion batteries, a new opportunity for circular economy and recycling. Also, you can find that information in the Critical Times, and it'll be in social media as well. We want to ask you again, any other additional topics, don't hesitate to put them in the survey. And again, also our guests for a great presentation that you can reach out to them individually, to their individual emails, to ask any additional questions that may not have come up in the Q&A. So thank you, everyone, and we look forward to seeing you next month.